So in this video, I'm going to look at problem 45 from chapter 22. So in this problem, we are given two thin slabs, two thin plates of charge. Their area, surface area, is 1 meter by 1 meter, and there's their equal and opposite charges on them. There's plus Q here, minus Q. Q is 15 microcoulombs, and their separation is given to be 5 millimeters. And they're asking, they're asking the force on one of the plates due to the other one in part A, and then in part B, if we take these apart by another further 5 millimeters to reach 1 centimeter, what is the work done? Okay, so first let's calculate the force. So they're asking for the force on one plate because of the other. Now this, on the face of it, looks like Coulomb's law, right? So you have two charges, they exert some force on each other, and you can just use Coulomb's law to do this. It's not that straightforward though, because these are not point charges, and Coulomb's law gives you the force between 2 point charges. And so what you can do is that you can take one little piece of this, some dq, and you can calculate the force on this dq because of this big plate that's negatively charged. And to do that, you need to divide this into little parts as well. So you calculate the force on this little part. Due to each and every one of those little parts, you integrate over that. And then you also need to integrate over this first original plate. So it will be a double integral. Okay? Now it can be done, but that's very tedious. Now there is another way to do this. What we can do is that we can write this force as some Q times E. Now this simplifies our matters immensely, simply because we actually know the electric field at this point, right? So the electric field between two parallel plates is something that is known. So we can just say that there's some electric field, and the electric field is going to have some sigma by epsilon naught magnitude. Okay? So can I just take that electric field and multiply by this and then integrate all over this plate? Is that something that's feasible? Yes and no. The problem here is that this is the strength of the electric field in between the plates. Okay? So outside the plate it's 0. In between the plates it has this value. But its value in the plate, that just at the point where this plate resides, is ambiguous. And in fact the charge resides at that point. So we don't know the electric field at that point. Okay? It's ambiguous. It's just not. It's not something we know. Now, why is it ambiguous? The reason is that the direction of the electric field produced by this plate actually flips sign as you pass over the plate. Right? On the right-hand side, it's going to be towards right. On the left-hand side, it's towards left. However, we do not care about the force applied on this charge because of the charges on this plate. Right? Now, why? Well, first of all, they're asking for the force due to the other plate. Right? So the question explicitly asks for something else. So you don't care. But on top of that, the total force that's felt by this charge on this plate, because of the charges residing on this plate, has to be 0. If it wasn't 0, then it could feel a force, then it will just move along this plate. And it will reach equilibrium somewhere else, and then it will be 0. Okay? Now, the force, because due to these charges, is going to be out of the plane. So yes, it cannot move because it can't leave the conductor. But the force due to these charges will be in the plane. So if there was a force, it would actually be able to move. Now we are in equilibrium, we are in steady state, so it's not moving, which means it actually does not feel a force due to the charges on the plane that it is on. Okay. But in any case, as I said, the problem is explicitly asking the force due to the second plane. So what we need to do is to take into account only the electric field produced by that second plane, and which means that the magnitude of the electric field is going to be something like this. Okay, so this is for a single plate, and we only need to take that into account. Okay, let us write this a bit more explicitly. To do that, I'm going to draw a coordinate system, something like this, over here, so I can actually have components. So this F is just going to be Fx is going to feel a force purely in the x direction, an attractive force towards the other plate. And this is going to be some integral of E dq. Okay? So this is going to be some of the little forces that this feels. So perhaps we can separate this into one more step. So this is going to be integral of d fx, and that d fx is going to be just E dq. If you want, we can also put a x over here. And what is that integral over? It's over the whole plate, okay, one of the plates. Okay, now what is the magnitude of the electric field that's produced by this plate over here that leads to this force that's felt by the charges on this plate? Well, it's given here. Okay? And that's a constant, so I can just take this out of the integral. So this is going to be sigma by 2 epsilon naught integral of dq over the plate. And what is the integral of dq over the plate? The sum of all the little charges that reside on the plate. If I add all these up, it's just going to give me the total charge. Okay? And the sigma is also the total charge divided by s. So this is q over s times q divided by 2 epsilon naught, and this comes to q square by 2 s epsilon naught, where s is just 1 meter square and q square is the square of 50 microcoulombs. Right? And you can check that the dimensions actually hold. So this is a force. It should look like charge divided by epsilon naught length square. This is charge divided by epsilon naught length squared. Okay, so that's an S. It's not a 2, it's not a 5, it's just the surface area. Okay, so this is the force. You can plug numbers in and get the numbers out. In the second part, they're asking what's the work done. Okay? So as you move this plate 5 millimeters more, in each 1 centimeter, what's the work done? So let's keep the force. We are going to need that. Okay. Well, the work done, strictly speaking, is going to be a line integral. PL for each and every one of these little parts, but we can also, integrate over this. So this is actually an integral over little forces and so on and so forth. But I think you can see that because these are moving in a uniform electric field that's produced by this positive charge, they're all going to do the same amount of work. So that integral over the little parts on this plate is trivial. Okay? And the integral itself is trivial because the force, as you see over here, has a constant magnitude. And in this case, the force and displacement are in the same direction. So if the force and displacement are in the same direction, then this dot product becomes a simple product. And if the force is constant, I can take it out of the integral. And then this just becomes F delta x, right? Something you probably remember from Physics 105. Right? And that F is over there, that delta x is just 5 millimeters, and this is the work done. Okay? I think they are asking for the work done by you. Yeah, this is work done by you, so it's going to be positive. So the force you're applying and displacement are in the same direction. The work done by the electric field, in this case, is going to be negative. The work done by the agent that's pushing the plates apart is going to be positive.